The forces you will use in your physics class when drawing free body diagrams and that you will use in this video are the force of gravity, the force of friction, the normal force of tension, and the applied force. The force of gravity can be abbreviated as Fg if you have Mr. Hansberger, or Mg if you have Mr. Gresh or Haberle. The others can be abbreviated as Ff, Fn, Ft, and Fa.
Because this video is just going over how to draw the free body diagram and not how to actually solve it, we're just going to pay attention to what forces are present and not really what the value of the forces are. So this example is straight out of our notes. It says a 150 kilogram crate is being pushed across a rough warehouse floor with a force of 500 newtons, and there's a frictional force of 20 newtons resisting its motion. So we know that the only information we really need to know from that is that its mass is 150 kilograms, which is not necessarily a force, but a lot of the physics teachers will want you to include that on your free body diagram. We also want to note that there is an applied force, which is that force of 500 newtons, even though we don't need to know it's 500 newtons. And there's also the frictional force present. So we know that we're going to have to include all those things in our free body diagram now. There's also other forces that you have to assume are present even though they're not included in the problem. So, for example, because the crate is an object on Earth, there's a force of gravity acting on it that we're going to have to include in our free body diagram. And also because it's on a surface and not in the air or being hung from something, there's a normal force of the ground pushing back up on the crate. So we're going to start by just drawing a square to represent the crate. Even if it wasn't a square, we could still draw a square to represent it. And then we'll write the mass of the object in the middle of it. So it's 150 kilograms. And then we know that the forces we want to add are the force of friction and the applied force. And those are the horizontal forces, and then the vertical forces are the force of gravity and the normal force. And just a few things to notice is that the force of friction is always going to be going in the opposite direction from the applied force and the direction that the object is actually moving. And then also, the normal force is always going to be perpendicular to the force of friction. Okay, and then the last thing that we're going to add on here is our acceleration. You just write that off to the side with the vector above it, pointing in the direction of motion. And that is how you do the free body diagram for this example. This example says, a girl pulls her little brother across the snow on a sled. The girl pulls the 18 kilogram mass with a force of 25 newtons at an angle of 45 degrees to the horizontal. So this example is different from our last example in that because the mass is being pulled by a rope instead of just being pushed directly, it has a tension force instead of an applied force. So that's going to be one of the forces that we have to include in our free body diagram. In addition to that, it also tells us that the mass is 18 kilograms, so we're going to have to include that in our free body diagram. And then again, we have to assume that there's a force of friction, there is the force of gravity, and there's a normal force. All right, so we're going to start by drawing our box and writing the mass inside, which is 18 kilograms. Then we can draw our horizontal forces, which are the force of friction going in the opposite direction as the tension force at an angle of 45 degrees to the horizontal. And then our vertical forces are the force of gravity and the normal force. And make sure when you draw the force of gravity that you account for the fact that there is a force of gravity on the kid in the sled and on the sled itself. And then finally, we're going to draw our acceleration, and even though the tension force is going at an angle, our sled is still moving horizontally. So still include the arrow, just horizontally above the acceleration, pointing in the direction of the motion. Our next example is different because instead of an object moving horizontally, now we're going to move vertically. So, a 70-kilogram man stands in an elevator, and after pushing the up arrow, the elevator accelerates upward at 1.5 meters per second squared. So the only forces that we need to include in this example for our free body diagram is the normal force and also the force of gravity, which are our two vertical forces. So we're going to start with our square and write the mass inside 70 kilograms. And then we'll do our force of gravity pulling down and our normal force going upwards. And then remember to draw your acceleration, and now they're accelerating upwards, so draw your arrow up. Our last example is an object moving at an angle. So we have a 20-kilogram block sliding down a 30-degree inclined plane. And the forces that are going to be present here are our force of gravity, the normal force, and the force of friction. So when we draw our box for this object, we want to make sure that we draw it at the angle it would be if it were sitting on the inclined plane like in the picture. So you're going to draw kind of like a diamond instead of a box. And then we can still write our mass inside, which is 20 kilograms. And then even though the object is turned because it's on an inclined plane, gravity is still pulling straight down. And then the force of friction and the normal force will stay perpendicular. Like we said in the first example, they're always going to be perpendicular. So they will come out here and here. And then lastly, we want to make sure we draw our acceleration, and it's going down at an angle, so draw your arrow going down at an angle.